Well, good morning from Canada and good afternoon, I guess, in Norway. So it's really a pleasure to be part of this workshop or conference. Today I'm going to be talking about reducing methane emissions from dairy production, and this is a topic that's always in the media in Canada and elsewhere. So greenhouse gases and methane emissions from animal production, we hear a lot about that. I'm sure you've all heard comments like, cow farts are ruining our planet. I'm a vegan. I want to do what's right for the environment. I think there's just so much information constantly being presented to us in the media, and consumers, researchers, farmers, I think there's a lot of confusion about greenhouse gas emissions. I'm not going to be able to clear up all that confusion in a half hour, but I want to give you some perspective on the issue, some of the main important components of this issue. So what I've done is I've structured my talk in two different parts. The first part is going to be about greenhouse gases from animal production. Where are these gases coming from? How much does animal production contribute in Norway and globally? And what are some of the reduction targets that we're trying to achieve? And then the second part of my talk will be about how are we going to be able to achieve such ambitious targets. So first of all, the main greenhouse gases from animal agriculture, there's three of them. So we have methane emissions. So we talk about enteric methane. That's the methane that's produced during the feed digestion process by the ruminant animal. So we have enteric methane. We have methane from the animal's manure. We also have nitrous oxide from manure and from the use of inorganic fertilizers applied to the feeds that are used to feed the animal. And then we have CO2 emissions from the use of fossil fuels in our machinery and in the use of inputs such as the manufacture of fertilizer and other additives that would be imported into the farm. And then we also have CO2 from soils. So CO2 from soils can be an emission, but it can also be a sink. So carbon dioxide can be stored in soils in the form of organic carbon when soils are managed properly. So we have three major greenhouse gases, and these greenhouse gases, using the International Panel on Climate Change methodology, are compared over a 100-year time frame, putting them on the same perspective to talk about their global warming potential. So methane is compared to carbon dioxide by multiplying by 25% to reflect its higher global warming potential when looked at over the shorter term of 100 years. So a cow producing 350 grams a day of methane would produce 350 times 25, 8,750 grams a day of CO2 equivalent. So that's the agreed upon methodology using the International Panel on Climate Change methodology. But there's a lot of discussion. That methodology was developed way back in the early 90s when there was, when the whole dialogue around climate and global warming began. But there's a lot of discussion about that methodology and how that may not accurately reflect these different warming potentials of the various gases. So let me explain what I mean about that. It's very difficult to compare methane from cows to CO2 from the use of fossil fuels. Fossil fuels, when we're using fossil fuels, we're extracting ancient carbon from the Earth's surface, we're burning that, and we're releasing CO2 in the atmosphere where it accumulates and lasts for hundreds and even thousands of years. In contrast, methane from the cow is part of a cycle. So we call this biogenic carbon or biogenic methane, because the CO2 in the atmosphere is extracted during the process of photosynthesis by the plant. The plant then becomes the cow's food. The food is then digested by the cow. Enteric methane is released and it goes back into the atmosphere in the form of methane. And that methane lasts in the atmosphere for about a decade, and then it's broken down. So it's broken down very, and on a short-term basis as compared to the hundreds or thousands of years of CO2 generated by the fossil fuel industry. So this is a cycle, and this cycle is in balance if cow numbers don't increase. And so that represents an actual opportunity for the dairy industry, because it means that if we can mitigate that methane or reduce the amount of methane or reduce cow numbers by having higher, more productive animals, we can actually decrease the methane concentration here, and we can actually have a cooling effect and compensate for some of the warming effect of the fossil fuel industry. So there's tremendous opportunity for the dairy industry to reduce methane emissions and participate in what we call a cooling effect on the environment. So let's look at Norway's greenhouse gas emissions. So I extracted these numbers from Norway's National Inventory Report in 2021. And we look at the sources of greenhouse gas emissions on a CO2 equivalent basis. Agriculture, which is both crop production and animal agriculture, represents about 8.4% of Norway's greenhouse gas emissions. And when we further break down agriculture to look at the sources, the agricultural emissions in Norway are about 50% coming from enteric methane emissions. So there's a lot of opportunity to reduce greenhouse gas emissions for agriculture by focusing on enteric methane emissions. How do the emissions in Norway compare to the global emissions? So in this slide, on the left-hand side, I've used the IPCC methodology that I used for the Norway emissions and looked at the agricultural emissions and the enteric methane emissions. They represent about 5% of total emissions globally. And in Norway, I said it was just over 4%. But we know that animal production is more than just enteric methane emissions. So we have enteric methane emissions, but we have emissions from, as I mentioned, manure management, from energy consumption, and from feed production. And we have both the production of feed, but we also have land use and land use change. So what do I mean here? When there's a change in land use, and in particular deforestation or removal of forests to produce crops for livestock, as in the Amazon, for example, there's very big concern about destruction of the rainforest. So we have a loss of carbon. When we put all of these sources of greenhouse gases together, it's estimated by the Food and Agriculture Organization of the UN that all of livestock contributes about 14.5% of global greenhouse gas emissions. And 20% of that is from milk production. So our greatest source is enteric methane emissions and from beef cattle, but certainly dairy also contributes to this. A lot of countries, including Norway, have set some very ambitious reduction targets in recent years. So Norway has committed to a reduction of at least 40% in greenhouse gas CO2 equivalents by 2030 compared to 1990 levels. And Norway has also signed the recent Global Methane Pledge, along with 120 other countries and partners. And this pledge is specifically oriented to methane, and the pledge states a reduction in methane of 30% by 2030 compared to 2020. So that's a huge, very ambitious target specific to methane. Right now, the focus is on the energy sector in most countries, including Norway, but second to the energy sector is agriculture. And so there's a lot of concern about what this means for methane emissions from animal production. And there's some very ambitious targets, and these targets are setting some very ambitious goals for livestock production. And in addition to these government targets, we know that a lot of companies in Norway and globally have set some very ambitious targets, talking about net zero by 2050 or very ambitious greenhouse gas emissions. So all of this pressure is being felt at the primary production level. So when we talk about reducing greenhouse gas emissions, there are really two targets. One is an emission intensity target, and that's the targets that a lot of private sector industries are setting. So that is the emission intensity, meaning reducing greenhouse gas emissions per kilogram of product. And this emission intensity target or carbon footprint allows the industry to continue to expand, but at a more efficient, in a more efficient manner. But if the industry does expand, absolute emissions may also increase. So governments are more interested in absolute emissions, so reducing the actual emissions that are being emitted into the atmosphere. So these two emission targets can act together, especially in countries where we're not seeing large increases in food production or animal agriculture. So the challenge then for agriculture is to produce more food, more meat, more milk for an expanding population, but to do this without adding to greenhouse gases, and in fact, in some cases, reducing greenhouse gases. So there's really three ways of achieving those targets. The first is increasing production efficiency. So getting more milk, more meat out of our animal production systems in a more efficient manner. The next is decreasing methanogenesis. So what is the opportunity for actually reducing the amount of methane that's produced in the animal's rumen during feed digestion? And the elephant in the room, the third way, is reducing demand. So reducing the demand for livestock products. Now, this is something that is more controversial, and it's not as straightforward as a lot of people would like it to be. So it means certainly there's opportunity to reduce waste. Now, waste in animal products is far less than in vegetable products. We talk about 30–40% waste in vegetable products. In animal products, this waste is considerably lower, both in the at the production level and at the retail, wholesale, and consumer level. And also there's opportunity to reduce consumption of animal products. We talk about vegetarian and vegan diets. However, that is an opportunity that is available, say, in high income countries where there's other protein products that can be substituted, but in many parts of the world that is not the case, and in many parts of the world we're already starting at a very low intake of ruminant products. So and also we have to consider that forage and byproduct feeds is the main feed for ruminants in many parts of the world, including Norway. And most of that land is marginal and not suited for crops that would be used to produce protein for human consumption. So it's not as straightforward as simply adopting a vegetarian or vegan diet, but certainly there is opportunity for reduced demand. So we, as animal scientists, we really have to look at opportunities to reduce methanogenesis. So these graphs I want to show you are often used to show the relationship between animal production, in this case dairy production, and methane emissions. And these are on a global scale. And this is from a study that was done by FAO some years ago. So on the left-hand side then, the graph shows the methane emissions per cow per year. And on the x-axis, we have the output per cow in terms of fat and protein corrected milk, so per cow. So as the amount of milk per cow increases, you can see that emissions also increase. So as a cow is more productive, emissions also increase, but it's not linear. It's curvilinear. So when we replot the data in terms of output of milk per cow per year, and then methane emissions per kilogram of milk, cows that have a very low level of production, what we might see in a developing country, have a very high emission per kilogram of milk. So that carbon footprint or emission intensity is very high. And as we increase milk production, that it decreases. So at higher levels of milk production, we still see a decrease in emissions per kilogram of milk, but the opportunity for improvement is much less. So in developing countries, the emphasis is really on improving the production systems, improving the diet, the genetics, the management to get more milk out of animals so that we can have fewer animals to produce the same amount of milk. However, that is still the case in developing countries, although the reduction per animal per year is much less. Why is that the case? My slide doesn't seem to want to advance. Oh, there we go. Why does increasing animal productivity lower greenhouse gas emission intensity? Simply, we need fewer animals to produce a given amount of milk. So we have less feed produced, and I mentioned that a third of the emissions are coming from feed. We need fewer replacement animals, there's less manure produced, and there's less methane produced because we have fewer animals. But on an animal basis, we actually have higher methane emissions per cow, but we have less greenhouse gas emissions per unit of feed that we're feeding. So animals consume more feed because they're more productive, but the feed is in the rumen for a shorter period of time, so less methane is produced. And we have a shift in the way the feed is digested, so we have more propionate and less methane. So overall, less methane produced per kilogram of milk. So in terms of actually reducing methane synthesis in the cow, there are also opportunities. The efficiency of a particular methane mitigation strategy depends on the effects in the rumen. The interaction between the rumen microbiome, the hydrogen flow in the rumen, because the methane is a sink for the hydrogen. And so all of these factors interact when we apply a methane mitigation strategy. And these factors can be affected by the diet intake, the composition of the diet, modifiers such as feed additives we apply, and the host animal genetics. So all of these factors interact to impact the amount of methane that is produced in the animal's rumen. And that methane that is produced then is breathed out through the animal's mouth. So 95, 96, 97% of the methane is released via the breath, and only a very small amount is released via the back end of the animal. And often we see in the media photographs of methane from the animal's rectum, but in fact that is not the case. Most of that methane is being released from the animal's breath. And because of that, there's a number of techniques that are used to measure methane in research that rely on measuring methane from the animal's breath. So there's a number of techniques. So we have animal chambers where we place the animal in a room for several days and we monitor the methane emission from the animal. But there's also techniques that can be used on pastures. We have tracer gas techniques. And we also have feeders that when the animal approaches the feeder, this is the commercial green feed system. When the animal steps into the green feed system, it receives a small amount of feed. And so the animal's breath is monitored over a number of days as the animal approaches that feeder. And there's also sniffers that can be applied in an automatic milking machine. So there's a number of various techniques that can be used in research. However, it is much more difficult to make those measurements in a commercial setting on farms. And each one of those systems has advantages and disadvantages, and more importantly, different levels of uncertainty. So, you know, a sniffer technique at an automatic milking machine would have a higher degree of uncertainty, for example, compared to a respiration chamber, but we'd be able to measure a larger number of animals in an automatic milking machine approach compared to, say, a chamber. So using those approaches, now there's now a very significant body of research that has been constructed, and we're starting to understand a lot more about what are the factors that affect the amount of methane that an animal will produce. And in this graph, I've tried to synthesize some of the dietary factors. So the most important factor is the level of intake. So as dry matter intake increases, the amount of methane in terms of grams of methane per head per day increases. So a dairy cow that's at a high level of intake produces more methane than a beef animal at a lower level of intake, even though the beef animal might be consuming a more fibrous diet. So at any level of intake, there's a lot of variation depending upon the composition of the diet. So diets that are high in starch, diets that are high in grains, or diets that are high in lipids result in less methane than diets that are high in fiber. So diets that are forage-based diets that are higher in fiber would have higher emissions than, say, a feedlot finishing diet that's based on grain. But within these diets, there's a lot of difference between forage-based diets depending upon the level of neutral detergent fiber and how digestible that fiber is in the animal's rumen. So because of this variation, then, there's a lot of opportunity to reduce enteric methane through diet reformulation. But here I want to stress that we're producing milk. We're not trying to produce methane. So the number one consideration has to be optimizing milk production. And most diets that are being fed on farms are already optimized to reduce milk production, to increase milk production. So when we're focusing on reducing enteric methane, we certainly don't want to reduce milk production. But for dairy farms, there's lots of opportunity in terms of diet reformulation, in terms of improving the quality of the forage. So forage quality offers a tremendous opportunity for dairy farmers. This is a study that was conducted in Denmark several years ago, and I use these data just to illustrate the importance of forage quality. So in this study, they had two diets, silage that was harvested early and had a higher in vitro organic matter digestibility, and then a silage that was harvested later that had a lower in vitro organic matter digestibility. And the impact of this difference in digestibility can be seen in terms of the dry matter intake. So the more digestible silage, the cows ate more silage, and as a result, energy-corrected milk increased. And because of the increase in energy, well, I should mention that enteric methane emissions measured in chambers, and this was grams per day, was not different between the two diets. And we often see that no difference in enteric methane emission grams per day. But because milk production and intake increased, the amount of methane per kilogram of intake or per kilogram of milk was considerably less for the higher quality feed than the lower quality feed. So by increasing the digestibility of the forage, there was a reduction in the amount of methane produced per kilogram of feed and per kilogram of milk. And that represents a tremendous opportunity for dairy producers. As I mentioned, there's also opportunity for lipids or fats. However, the opportunity is much less. Adding lipids to the diet can decrease methane emissions about 3 to 5% per percent added fat. However, most diets already contain some degree of added fat, so there's limited opportunity for further additions of fat, but this can be the case in some farms. However, we have to be careful because higher fat diets can reduce fiber digestion. So there is a limited potential to add fat, but added fat can reduce methane emissions by 10 to 15% in most for most diets. A lot of interest in the potential of using feed additives to reduce methane, and that's an opportunity for dairy farms where we're feeding partial mixed diets or total mixed diets, because those feed additives can be simply added to a diet without changing the diet or reformulating the diet. So here I show some of the additives that are of interest. There's some, I'll talk more in detail about 3-nitroxypropanol and seaweed, red seaweed, but there's also interest in plant components such as tannins, and direct-fed microbials and other phytocompounds. And this area is an area of active research in a lot of labs. There's a lot of interest in this, but right now we do not have commercially available feed additives that reduce enteric methane emission. So I'm going to focus on 3-NOP and Asparagopsis to give you a greater perspective on those three additives, simply because the opportunity is much greater for 3-NOP and Asparagopsis in terms of the magnitude of reduction possible. So 3-nitroxypropanol is a compound that has been developed recently by DSM Nutritional Products, which is a company based in Europe. And this compound interacts with the biochemical synthesis of methane in the rumen. It doesn't kill the methanogens, it just interacts with the reductase that's involved in the synthesis of methane. And studies have shown no residues in meat and milk. So because of that, the product recently was approved in Brazil, Chile, and most recently in the EU. So the current formulation of 3-NOP needs to be added to the diet, so it's not something that can be used on pasture yet. So there's a lot of studies now published on 3-NOP, and in most of the studies, the dairy studies, we're seeing about a 30% reduction in methane, and it is a dose-dependent response, so at higher levels we get higher reductions, but mostly around 30%. And it's less effective in a high fiber diet and much more effective in a high starch diet. In some of our studies in Lethbridge and high starch feedlot diets, for example, we're seeing up to 80% reduction. But the thing about it is a lot of research showing now that it can be effective over a long period of time, and there's no major impacts on milk production. So no improvements in milk production in most studies, but also no decreases in digestibility and no decreases in milk production. The other compound that we hear a lot about in the media, very exciting compound, is Asparagopsis taxiformis. This is a red tropical seaweed that is not native to northern oceans. It's produced in Australia and Hawaii and some parts of the Mediterranean. But it can also be grown in tanks and then dried down and extracted. It also blocks the last step of methanogenesis in the rumen using a different pathway. And in studies, it has been shown in vivo to reduce methane emissions by up to 90% in beef. But there's certainly at this point a lack of experimental data on what happens to animal production, especially at these high levels of methane reduction. So it's something we're going to hear more about in the future. The bioactive component, though, is bromoform. So bromoform is a halogen, just like chloroform. And there is some concern because bromoform is at least in the US, is classified as a group 2 probable human carcinogen by the EPA. So meaning if there's any residue of bromoform in meat and milk, that would be a concern. So in most studies so far have shown no residues in meat and milk. However, that's something we need more research on. There's also concerns that in this, in its native form, in the seaweed, the bromoform after harvesting can decline, so it can decay, as it also is degraded in the rumen. And the other concern is there's emissions associated with harvesting and producing this as a feed additive that may offset some of the reduction we're seeing in methane emissions. And it is very expensive in the current way of producing this as a feed additive. So while it's very exciting, there's a lot of hurdles that still need to be addressed in research and commercial production. There's a lot of talk about, if we decrease methane emission, methane is a loss of energy from the animal. So if we decrease methane emissions, would that actually improve animal performance? And I would say that in most studies, especially with 3-NOP, we're not seeing an improvement in animal performance to any large extent. And I think we have to look at that more critically. When methane emission is a loss of energy, so about 6-7% of the gross energy that we feed to animal is lost in the form of methane that goes up into the atmosphere. So if we reduce that loss of energy by, say, 25-30% using 3-NOP, in theory, that should mean we have more energy retained for milk production. But that's only on paper, because that assumes that there's no reduction in digestible energy, which we're not seeing a reduction in digestibility with 3-NOP. That may not be the case with lipids. It also assumes no reduction in feed intake, which may not be the case. Often we do see a small reduction in feed intake. And it also assumes that that energy would be captured in other energy substrates, such as propionate, that could be used for milk synthesis. And that isn't always the case, because sometimes we see a loss of hydrogen that isn't captured in the rumen in terms of hydrogen sinks. So I think in the early days, we sold this whole concept of reducing methane emissions as a way of increasing production. But I think we have to rethink that and be honest with our farmers to say that we may not, in fact, be providing more energy to cows. It may not mean improvement in production. It may just simply mean a reduction in methane, which is good for the environment. And then there's a whole question of who is going to pay for that mitigation strategy. So finally, the last thing I just briefly want to mention is today I've talked a lot about animal diets, but there's also potential in terms of other strategies. I briefly mentioned the whole area of animal genetics. There's a lot of interest in, can we select low methane emitting animals? We know that it's moderately heritable methane production. So there's a lot of interest on whether we can select low methane producing animals. The challenge there, though, is getting a very accurate low methane phenotype for a large number of animals. So that is very difficult, because measuring methane emissions from animals can be very challenging. So that means working across countries and working with a large number of animals. So it's something we're going to see more about in the future. What is the opportunity? Maybe 5 to 15% decrease in methane emissions by 2050. But that's still on the research platform, something that we're going to hear more about in the future. So I just want to make some very final closing remarks. So governments, private sector have set some very ambitious targets, and these targets are going to increasingly put pressure, and they're already putting pressure on our livestock production systems to lower greenhouse gas emissions. And so to lower emissions, the carbon footprint of milk production in Norway and the global north is already low, but there's certainly further opportunity to continue to reduce. The focus has to be on reducing enteric methane, because that's 30, 40, 50% of the footprint at the farm gate. So it's the largest component, and reducing methane can have some very immediate impact on decreasing the temperature rise. So there's a lot of focus on methane. There's very limited options right now for our producers. So when farmers ask me, how do I reduce methane emissions? Right now, farmers need to focus on improving production efficiency, increasing forage quality, increasing diet quality, and herd management to get to minimize the number of less productive animals that we're carrying. So there's no single approach. We need to combine strategies, and we're going to see this in future years. So better herd management, better feed quality, diet reformulation, the use of these new feed additives that are coming on screen, improvements in animal genetics. So to meet those targets, we're going to have to really seriously ramp up our investment in research. We have come a long way, even though there has been, I think, relatively small investment in methane mitigation research. We need to look at vaccines, new feed additives, and whether we can actually reprogram the animal's microbiota in a manner that would reduce the amount of methanogens or the amount of methane being synthesized in the rumen. So with that, then, I thank you for your attention and appreciate your interest.